do them a little bit different in statistics because, number one, you kind of have a background of a little bit more probability. In Algebra 2, you didn't, and it's calculator driven here, so I used the calculator a little bit more. And I did try this when I was teaching Algebra 2. I did try it one year, showed it to the fifth grade, but they didn't have enough probability background, so you guys will kind of see it a little bit differently. Yeah, I know, it drives me crazy, I know. You guys can move away from there. Don't sit, I mean, that's the going right by the chair. So if you guys want to move to the other side, so it's not sitting by you. Okay, now, before we said, to be a probability distribution before the break, we said two things had to happen. Number one, it had to be, your probabilities had to be between 0 and 1. And 2, they had to sum equal to 1. I'm sorry, you can't hear me?
Not really.
Oh, yeah. I'm using my loud voice. Only when I yell at my dog. Okay, and my grandson irritates me. Because no to him. Because I'm always yelling, stop barking, no barking. And my grandson is like, no, all the time. Yes, I yell at him. Okay, so before the break, we talked about, to be a probability distribution, two things had to happen. The probabilities had to be between 0 and 1, and the sum of all probabilities had to equal 1. Now, this time around, we're talking about a binomial. Bi means what? As a prefix, what does it mean? 2. So, you did binomials in Algebra 2. I know. Who took the books away? Because I thought the books did a little... That was my book. Oh, okay. So let me try another book there. So that people...
We're just got to cover the whole thing.
Okay.
I think it's over there.
I think it's like metal now on metal.
I might have to see.
No, it looks like one of those pencil things.
Don't take your fingers in there.
Good.
I can't. It's black. It's black. All right. So a binomial says two things have to happen. And I honestly, whoa. All right. Let's see if this works. Okay, but it's a little bit less. Oh, great. Big difference. Ah, thank you. Oh, big difference. Thank you. Thank you. That made a big difference. So, our binomial says two things have to happen. Two possible outcomes. We call this a success and a failure. And you did this in Algebra 1. And in Algebra 1 and Algebra 2, you did this. You said, say you were going to run this, say you went on vacation, this is the famous one. You go on vacation for 5 days. The probability that it's going to rain is 30%. If you want to know what is the probability of exactly 2 days raining, you did this. I measure my success, 3 days, 30%. I want 2 of them. Then you subtracted, then you did the rest. This is how you found your binomial probabilities. There was only 2 things that could happen, rain or no rain. So I say yes to rain, no to rain. I say yes and no, black and white, whatever 2 possibilities can happen, only 2. And sometimes we have to use your complement condition, because sometimes you'll have like a jar of marbles, and you'll be like 5 red, 3 blue, 2 yellow. If I want the probability of just a red, I have to combine my blue and yellows, because it can only be 2 choices. So it's going to be a red or not red. So that's how we look at binomials. It could have more than 3 things there, more than 2 things. We just have to combine them to make ourselves 2 outcomes. So this is important right here. These 4 things have to be present for you to do a binomial probability. The experiment is repeated for a fixed number of trials. This is your N. Put this on your notes. This is your N. Where each trial is independent of the one before. It's not going to change the probabilities. Probabilities will not change. There are only two possible outcomes. We call them a success and a failure, a yes and a no. The probabilities of success are fixed. They never change. If they change, it ruins our whole binomial. And the random variable x discounts the number of successes that we get. Notation. N, again, is for the number of trials. P is the probability of success. Q is the probability of failure. And X is your random variable. So if you see the P and the Q, the R and the X, this is where they come from. We're going to work a few of these out, but I just want you to get used to what you're looking at here. All right. So a certain surgical procedure has an 85% chance of success. A doctor performs this procedure on 8 patients. The random variable will represent the number of successful surgeries. Each surgery he does is independent of the one he did before. Everything's a new case. Nothing affects the one before. So the first thing we say is this binomial? Can two possible outcomes happen? What are his two possible outcomes? It's failure and success. The operation was a success, the operation was a failure. He has an 85% chance of being a success. Is that going to change with each operation? Each operation is independent of the one before. So, what's your N? How many operations is he going to perform? How many patients is he going to work on? 8. So he's going to perform 8 operations. What's the probability of success? 85%. That's fixed. It's not going to change. What's the probability of failure? 15. This is 15 because it's 1 minus. This is because we only have 2 outcomes. Either he's successful or he fails. And X is going to be all the possible successes. So what can my X be? From what to what? From 1 to 8 or 0 to 8? 0 to 8. Can he have no successes? Hopefully not, but possibly he can have no successes. I certainly wouldn't choose this doctor, but he can absolutely have no successes. Okay? So these are the things we're looking at. What we're going to do is build a table. And eventually our table's going to look like this. All the possible outcomes that could happen with this. We're going to build them. Right. Now, we can try another thing, just to see if this qualifies for a binomial experiment. A jar contains 5 red marbles, 9 blue marbles, 5 red, 9 blue, and 6 green. You randomly select 3 marbles from the jar without replacement. The random variable x represents the number of red marbles. Okay. Without replacement. So let's talk about this. What are our 2 outcomes? It's going to be a... What color am I looking for? Red or not, right? So do I have 2 outcomes? I have 2 outcomes. I have a success and a failure. How many times am I going to do this? How many marbles do I want to select? 3. I got an N. Okay, so far so good. What is my probability of success? How many total marbles do I have? 20 marbles. What is the probability of a red? 5 out of 20. What is the probability of not a red? 15 out of 20. So far, so good. But if I choose a red and I don't replace it, what happens to my probability? If I choose a red and I don't replace it, so now I have 4 reds and 19 left. What happens to my probability of choosing a red? It went from 5 out of 20 to what? 4 out of 19. Does this qualify to be a binomial experiment? 4 things have to happen. Probability of success or failure. We do. We have a red or a not red. We can loop these two into a not red. Probabilities have to remain fixed. Did they remain fixed? No. What caused them not to be fixed? You didn't replace it. Without replacement means you kept it out of there. If I did replace it, would that be a binomial experiment then? Would my probability stay fixed? And then I could get 0 reds, 1 red, 2 reds, 3 reds, 4 reds. I can't get more than 3. Because I'm only doing this 3 times. Does anybody see the difference? When we look at a binomial experiment, those 4 things are what you have to look at. What I find it easier is if you do this. Find your N, your P, your Q, your X. If you can find all those, then chances are you have a binomial. If you can't find something there, or you see something that's wrong, such as this one, the probability changed on you, and you had to change your P, that can't happen. So that's what you have to look for. Take a minute and you guys look at this. You try this one. Sounds like a plane. So, do you think this is a binomial experiment? Does this qualify? How many say yes? Kinda, sorta. Steven's kinda. We'll see how many people raise their hand. How many say no? Okay, so let's take a look at this. You take a multiple choice quiz that consists of 10 questions. Each question has 4 possible choices, A, B, C, D. Only one is correct. To complete the quiz, you randomly guess the answers to each question. The random variable x is the number of questions you get right that you answer correctly. So, what's n? How many times are you doing this? How many questions on your test? 10. What's p? The probability of doing what? Getting it correct. This is the probability of guessing a correct answer. What is that probability? 1 out of 4. Is it going to change for the next question? Isn't it always going to be 4 choices, 1 will be correct? So your probability stays fixed. This is what I need to know. It is fixed. So what is the probability of not getting it correct? That you get it wrong. 3 out of 4. This is your complement case. 1 minus this. And what does x represent? The number of answers you got right. What can you get right? So on 10 questions, 1 out of 10, can you get 0 right? And can you miss them all? So this represents 0 through 10. 0 is the one that's most missed, because like sometimes you have a 0, sometimes you don't have a 0. If you're figuring out things that are countable, you have a 0. If they give you like the grading of something, well, they probably don't rate it with a 0, they rate it with a 1 or not a 1, or something like that. But most of the times you're going to get 0 in these, because 0 means none of them happen. So therefore, is this binomial? Yes. This qualifies for being binomial. Okay. This little lovely thing was what you guys used in Algebra 2 when you had to find your binomial probability. It really wasn't as bad as it looked because, say for instance, the last one, your probability of success was 1/4. Your probability of failure was 3/4. Your n was 10, right? So if you wanted to do exactly 3 right, you would do this. You would say, out of 10, I want 3 of them to be right. I always measure success before my failures, so my success rate is 1/4. I wanted 3 of them. My failure, therefore, is 3/4. And if I got 3 right, how many did I get wrong? 10 minus 3, 7. This is what you put in your calculator. Remember doing this? It's just a pattern. If you had to do at least 3, then you had to do 3 plus the 4 plus the 5 plus the 6. You had to string them all out. On the Regents, it was always like a 3 or 4 point problem, like a fastest score. So this is what you did, and it doesn't work any differently here. However, we have a little calculator thing that will do this. We have a nice little calculator thing that will work for this. And in your calculator, you guys have your calculator handy? If we can hear it over this. Okay, if you hit second there, and you come down to the word binomial. Hang on. She does. This is the best floor to work on. She keeps a beautiful floor. Okay, so we have this nice little thing in here, and hopefully when you do this, yours is going to look like this. The number of trials, this is your n, this is your probability of success, this is your x value. Okay, now we have 2 things. One with the CDF, one with the PDF. Now the difference here, and I'll go over these again, we'll do them again. The PDF is the one we're going to mostly use. We're going to mostly use it. I hit it again. I don't know why I keep hitting the wrong one. Oh, because it's getting so loud in here. Okay. PDF will find each individual one. PDF just means cumulative. So it'll accumulate. So when we need to do an outreach or an at most, you can use the PDF. But we're going to use the PDF, and it's going to ask you for the number of trials. It's going to ask you for the P. It's going to ask you how many do you want to be in this. And it will calculate it. And you will not have to use that at all. So let's give this a try. Let's do one, guys, and that'll be good for today. So a rotator cuff. A rotator cuff surgery has a 90% chance of working, of being successful. The surgery is performed on 3 patients. Find the probability that the surgery is being performed successful on exactly 2 patients. That means out of 3 patients, I get 2 successes. What's the probability that out of 3, I get exactly 2 successful? So first we decide if it's binomial. So we start like this. Everybody write it down on your paper. Okay. We're going to do this both ways. How many surgeries am I performing? 3. What is the probability that it will be successful? 90. What is the probability that it will not be successful? 10. So do I have 2 things that can happen? A good or a bad, a success or a failure, a yay or a nay? Now my X. Can I have no successful surgery? One successful, two successful, three. Can I have four successful surgeries? No, why not? You only have 3 patients. So you can have no success, one success, two success, three success. Now you want exactly 2. So this is my X. This is my probability. I can have 0, 1, 2, or 3. All I care about is this guy right here. Now, in algebra 2, you did this. 3 things I want you to be successful. My probability of success is 0.90. I want 2 of them. My probability of, I always want to be successful in life first. I always count my successes first. My probability of failure, 10. So I want how many is going to be left over? 1. And you put this in your calculator. So, huh?
You start a vote with that.
I know, isn't that terrible? So we did this. Yeah. Let's put this in your calculator first. I know it's hard, guys. Just try to stay with me just for a little bit. So you put this in your calculator. Do you remember doing this? Right? 0.9. How many did you want? 3. Then you had 0.1. How many did you want? Oh, sorry, you wanted 2 over there. 2. I don't function well with that noise. And you want 1. So we put this in your calculator, and we got 0.243. Now, this is what we're going to do instead. We're not going to do that. We're going to do this. Everybody grab your couch. Second, there. And now we're doing a binomial. So come down to see the word binomial. And I want you to stop right at this one. Binomial, probability, distribution, function. That's what this means. You should have this software on your calculator. The number of trials, how many patients did we see? 3. What was my probability of success? 0.9. How many successes do I want? 2. And paid. That's what it's going to look like, and that's what I get. Now, eventually we're just going to do this for everything. If you were doing this, you'd have to keep changing this. You'd have to say this. 3, 2, 3, 0.9, 3, 0.1, 0. Right? You have to keep changing. Everything changes. This changes, this changes, this changes. For us to do your binomial probability, watch what we do. Okay. See what that you just did? We're going to put this in here. Say I want 0 successes. All you have to do is this. Second, enter. That's my how many times I did it. That's my probability of success. That's my F. Change that to a 0. Hit enter. That's my answer. Now, it says 1. My probability can't possibly be 1 because all my probabilities have to add up to 1. What does this mean? E to the negative 3. Move your decimal 3 places to the right. So this is going to be 0.001. It's still a probability distribution, so they have to add up to 1. Okay? Second enter. Change this guy to a 1. 0.027. Second enter. Change this guy to, I'm just filling in your table, a 3. Yeah, 0.729. That's how easy this is. Whoa.
Good thing. Okay. Saw like something spilled. I thought it blew up.
I'm just hoping nothing comes flying out of there. Don't tip your boat there.
I'll sue. So it's good. I'll be rich.
Whoa.
Sue it.
Okay, so now, what should all these probabilities add up to? 1. Because if this is hang on one more minute, guys, a binomial probability distribution function, the two things that had to happen was my probability has to be between 0 and 1, true, to be a probability distribution function, and the sum of all my probabilities has to add up to 1. To make it a binomial means I had to add this part to it. The choices, fixed probability, n number of trials, x is my successes. So now, look at how much easier this is. If I want to say what is the probability that at least 2 are successful. Before, when you did this, you had to do 2 plus the 3, right? Now all you have to do is come here and add up those 2 probabilities. So it doesn't look as bad, does it? A little bit easier than what we did in Algebra 2. Now, again, I tried one year to show my Algebra 2 kids this, and there are some kids that get it, so every year I showed a few of them. But because they didn't know enough about the probability distribution function and, success and failure, this was a little difficult to work this part out. But all my statistics kids that have to retake the Algebra 2 do this when it comes to that problem. And I knew that because the first time that I showed my statistics kids this, and one of my kids retook the algebra in January, I was in the grading room, we were grading, and somebody said, look at what this kid did for this probability. So I walked over there to look at it. I'm like, yeah, that's my statistics kids. This is absolutely fine to get there. So it's allowed to do it, because now you have a better understanding of it, and you'll use this way instead of the other way. Everybody kind of okay with this? We'll try another one. But are you good with this? All right. It's really not that bad. All right, what I want you to do right now is just take this and see if you could just set up the N, the P, the Q, and the X. And we'll work it from there. Okay, so 2 things. This is called a binomial probability distribution function. It is a mouthful. It has our existing probability distribution function in there, in that mouthful. Jack told us it had to have 2 things. Probabilities have to be between 0 and 1, and the sum of all probabilities has to be equal to 1. The binomial part tells us, you have to have 2 choices, only 2 outcomes, success and failure. You have to do this n amount of fixed times and trials. The probability cannot change, and your random variable has to measure all the successes. They both have to occur at the same time. So what's the n for this guy? 5. You're doing this a total of 5 times. What is it you want from this experiment? what do you want to pull? You want to pull 3 clubs. You're going to do this 5 times, but you want to pull each card you pull. Can you pull 3 clubs at the same time? So you're going to pull 1 club, right? So what is the probability of pulling a club? How many clubs are in your deck? 13 out of 52. How many suits in your deck? 4. And you want a club. So, would we say 1 out of 4? 13 out of 52 reduces to 1 out of 4. And if it's not a club, I don't care whatever else it is. This is my complement case. I got 3 other suits. Doesn't that make sense? 3 other suits, but I still have 2 outcomes. Club, no club. These are my 2 outcomes. I grouped them all into one, my other 3 suits, but I still have 2 outcomes. I don't care what it is, a heart, diamond, spade, I don't care what it is, as long as it's not a club. How many times am I doing this? What is my X going to represent? How many clubs can I get? Can I, in my 3 cards, can I get no clubs? Can I get 1 club? 2, 3? Can I get 6 clubs? No, because I'm only doing it 5 times. So do we agree that it's a binomial distribution? Okay, so we're going to set our chart up. I get it, we don't have to do it because all we have to do is exactly 3, but I like you to get used to doing it. Run these X values right along here. Now, first time through, you're going to set this up. You're going to say second vers. You're going to come down to the word binomial probability distribution. Right there, the first one. It's going to ask you for the number of trials. You have it, but it's n. 5. What is the probability of success? 1/4, 0.25. I'm going to put in 1/4. All it takes, it can find the few. It can do the 1 minus that. It doesn't care. And I'm going to start it at 0. And I'm going to paste. You can put in 0.25. Round your probabilities to 3 decimal places. So 2.37. 0.237. Sorry. Now, all I have to do is this. Watch. Second enter. Which one am I going to change? On the right, I'm going to change the 0. My n is going to stay the same. My probability of success never changes if I don't have a binomial. Now I want 1. So I say, 0.396. I'm just going to run it down again. Second enter. I'm going to change this guy to a 2. Look how much easier this is than what you did in Algebra 2. 0.264. And granted, we only wanted the 3, but I wanted to run all of these down. Let's just finish this up. 3. 0.088. Guys, don't pack up yet. Just give me 1 more second to finish this. 4. 0.015. And 1 more. 9.6. Is that my probability? 9.7. Is that my probability? Can't be greater than 1. Look at that. Move it 4 decimal places. I get 3 zeros. Go out to at least a significant digit. Even 9 or 0.010 if you want. At least a significant digit. 3 zeros. Sorry, 3 zeros. Okay, so now can I find my exactly 3? Right here. Good work, guys. Thank you for being cooperative with that thing.